gonna go live, okay?
Okay. You record?
1 second. Yep. Hold on, record. We good? All right. Hello, everyone. Welcome to this brand new episode of Quadcast. I'm your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome, welcome, everybody. If you are watching this past the point of live, do we do this every Tuesday at 5 p.m. So 5 p.m. Pacific time. So do join us if you can. If you haven't already, also join our Discord channel so you can ask us questions there. And if you're watching this on YouTube, please do ask us questions and so we can get to them during the episode. So without further ado, I guess Mikey, one question I was thinking about is like, you know, about the interior of a black hole. Like, I've heard it exists, it doesn't exist. I've heard mixed perspectives on it. Like, what happens when you fall in? Just shed some light on that. I'm gonna throw this broad question at you.
If you heard that it doesn't exist, you must have been talking to some high-level physicist because that's like it's a weird thing, right? Like it's a weird question. Does this object have an inside? Do we have any other example of an object that doesn't have an inside? It seems like a silly question, right? Um, and I think that's kind of the crux of what has been plaguing physicists for better the last 50 years is that every single attempt to describe the inside of a black hole in a way that is consistent with what we see on the outside just falls flat on its face. Like the equations just don't make sense, violates principles that we know have to be true. So there's something very, very strange about the surface of a black hole that is unlike the surface of any other object that has led physicists to question whether or not the inside actually even exists, which is kind of crazy if you think about it, right?
Wow, that's very bizarre. Like, I thought I've seen like in many videos, like, oh, this is what happens. You fall into a black hole, you get spaghettified, and like cross the event horizon, nothing happens. And Interstellar, right? Like, what? Why isn't there an interior? What's going on?
Ah,
Can you give more concrete examples of
yeah.
like, what
So
do you
the things
mean?
you're
Yeah.
describing, yeah, the things you're describing, like you know, before maybe like 20 or 30 years ago, everyone thought that they understood how black holes worked. They thought that Einstein's beautiful theory about curved space-time, called general relativity, everyone thought that that was a description of how black holes worked. Um, and so from that description, if you believe Einstein 100%, then you can absolutely fall into a black hole and you can absolutely predict what will happen to you. You're going to turn into spaghetti, as you call it.
Hmm.
You're going to be stretched out into a noodle, basically, and then you're going to hit what some people call the singularity. Um, but there's actually a lot of problems with that description, and I think most people in the know no longer believe that could possibly be true. First of all, there's no way that there's actually a singularity in the middle of a black hole. That's highly suspect. In physics, when we see something like a singularity or an infinity, it's always a sign that there's some new phenomenon that we don't understand, and that we have the picture wrong. That happens time and time again. So I don't buy that. Um, and yeah, but more recently, particularly when people started to understand quantum mechanics a little bit better, they started to realize that the quantum mechanics does not, it's very contradictory to this picture that Einstein had
Yeah.
that you can describe a black hole in this way.
Yeah.
So I guess one question I have before we like move to the quantum mechanical explanation is like what I mean like there was a dude named Schwarzschild, I think back in like World War I, who like found out these objects by assuming there was an interior that exists and it predicts like the exterior of a black hole, like the properties of it and whatnot. We see that in astrophysics and cosmology and astrophysical studies. Like what gives like can we go a bit more into that?
That's key, yeah. But by the way, he did this while he was literally inside the trenches.
Yeah.
Like literally sitting in his notebook while he's in the trenches getting shot at. Um, but um, what was I going to say? Yeah, so like I think you touched upon the key point is that what Schwarzschild discovered was the existence of this singularity object, or what
Mhm.
looked like a singularity, but probably not. And that kind of implied that there is a surface, this exterior, which we can actually see.
Hmm.
And that's, yeah, so he discovered something kind of nonsensical, but it tells you something about the surface of the black hole, which we can actually observe. Uh, so I would say that what Schwarzschild discovered was kind of the first hint that something funny is going on,
Mm.
based on this idea of what's inside the black hole, and it doesn't really make sense.
Yeah, I would say that Schwarzschild, what he did was he basically took Einstein's theory of relativity and he ran with it, right? But the problem
Hmm.
is, once you come up with a solution to Einstein's equations, that solution better fit in with the rest of physics, because physics isn't just Einstein's theory. And then
Hmm.
scientists start to think about, hey, how does this solution play well with, say, quantum physics or thermal physics, right? And one of the key observation is that when you have a black hole, you have this surface called the event horizon, where many people are familiar with. It's the point of no return. Things that fall in, you can never see it coming back out. There's no escape. Not even light can escape. But then, if you take a picture of the black hole, and in fact we have a picture now, looks something like my background. We do have a picture of the Horizon Telescope. We took a picture of the black hole. It always looks like that there is a blackness in the middle, right?
Hmm.
So even though theoretically things can fall in, you can never see those things basically falling in, right? Because they never
Hmm.
escape. And as a matter of fact, you will never see something falling into a black hole, and you only see it getting closer and closer and closer to the surface. And the question is, if something, if like, and if you're just standing on the outside of the black hole, it's almost like there's no way for you to confirm that the interior exists. And the only way to do that is for you to actually go into the black hole, in which case you can never come back out to tell the tale, unlike what movies try to portray that, right? So it's like if you couldn't smell something, you couldn't detect something, and and there's no other hint that it exists other than kind of theoretically, then the question is, well, then does it really exist, right? So here's kind of the
Can we
question.
wait? Can we unpack that a little bit? Just 'cause I think actually I didn't realize that this is kind of an important point. This is, as Tim mentioned, this is kind of like a hint that something funny is going on, right? Because if you do believe Einstein completely about what happens when you fall into a black hole, which we shouldn't, but if we do, it tells you something kind of suspect, right? According to Einstein's theory, space and time stretch uh, as a response to a large, massive object. And a black hole is so massive that um, at the surface is basically the point where time stretches so much that it basically slows down to a stop if you're an outside observer. So if Tim was falling into a black hole and if I was watching him from the outside, those signals of Tim falling into the black hole would become so stretched out that I would actually never see him fall in. He would like start going in slow motion and then slower motion and slower motion until eventually he would just freeze on the surface. So everything that's ever fallen into a black hole, from an outside observer, basically just looks like it's painted on the surface and frozen because the time, according to Einstein's theory, the time stretches so much that you actually just freezes.
Is there any intuition you can give about like the time stretching? Like what does that mean? Like how can I like visualize that, or how can I wrap my arms around that space and time
Anytime you're
stretching?
close to a massive object, time slows
Hmm.
down. So like time moves more slowly on Earth than it does like far from the Earth, like on
Yeah.
satellites. GPS systems need to take this into account if they want to get better than like a kilometer accuracy. So it's a very real effect. If you're close to a massive body or if you're moving fast, time slows down.
Yeah, so I
Um,
guess
Mm.
Interstellar demonstrated this, right?
Very well.
Spoiler alerts, but if you get really close to a black hole and somehow were able to make it out alive, let's say you didn't go in, but you kind of like skirt around the outside of the event horizon and you came back, for you, maybe like, oh, maybe only like a year passed, but when you come back, it's gonna be like many decades. All of a sudden, time has elapsed on Earth, for a long time. So this is the effect that we're talking about, right? It's almost like an
It's a
ET.
measurable effect. Measurable
It's a
effect. There's no
measurable
question
effect,
about this,
right? Yeah.
and we
Wow.
have measured it.
Yeah, so you mentioned things getting like plastered on. So if think if you never see anything going into a black hole, it seems that it's questionable whether interior exists or not. But like, where does that leave us? Like, what do we do? Like,
What do we do? That is the
yeah.
question. That is a question of the century.
I mean, there is one resolution. Should we talk about it's the principle of complementarity, right?
Right.
Yeah.
Yeah.
So that is kind of like a generalization of Einstein's concept of relativity. Basically, his idea is that different observers could see a slightly different reality, right? Like when, for example,
Wait, not could. Different observers will necessarily see it. Like different observers cannot agree on anything, right?
right, sure, yeah. According to the theory, yeah, different observers have different sense of reality. But usually in Einstein's theory, this applies to the sense of space and time, right? It's like, hey, if I'm close to the surface of the black hole, the rate at which my clock ticks will be different than the rate at which a different clock ticks somewhere else. And if we were to send signal to each other, we'll notice a discrepancy, right? But then this idea of complementarity takes it, I think, one step further to a more extreme version. Is that the idea is that whether the inside of a black hole exists or not may actually depend on your perspective. That to some observers maybe it doesn't exist, and to some observer it does exist. So that's kind of the idea here.
That
Yeah.
that
So
sounds like
Einstein's theory of relativity, right? Einstein's theory of relativity says that your reality depends on your perspective, and the step further is that whether or not the black hole interior exists depends on your perspective.
that that sounds I don't know, that sounds a little bit like a cop out to me. Can we
It's a little.
like
I
can
was
we
thinking the same thing. Actually,
yeah.
it's a cop out. It's a cop out for now. Like in the absence of true understanding, which we're working towards. I would say it is a bit of a cop out. You
Yeah,
know,
but it's not
to not be a
crazy,
cop out, you have
right?
to explain. Yeah, you have to
But
explain how this happens
yeah,
to not be a cop out.
yeah, but the fact that this is actually not obviously contradictory, that's kind of insane, right? Like I said
The fact
before.
that you could never prove the contradiction gives it some weight.
Yeah, exactly. Like if something's like imagine something in the real world is so obviously contradictory. Like let's say there's a crime and two witnesses say two different things, right? They're gonna come together and argue it out. Like someone is lying, right? You cannot just have two truths, right? But the problem,
Mhm.
but the thing here is that if you let's say you have two witnessing a black hole, let's say the one that I'm showing you in the background, someone on the outside says there is no inside of the black hole, and let's say Sahil, you disagree, you jump into the black hole, be like, I prove you wrong. There is the inside of the black hole. You and I, we're not gonna find out. We're not gonna come
You
together
can't.
and
You
disagree,
can't. No, you
right?
can't. You can't verify it. That's the point. Yeah.
Yeah. So I guess how would you so you mentioned the word complementarity. Like why is that word relevant? Like what does that actually mean? Why is it called complementarity?
It basically means that there's two ways of seeing the same thing, right? And I just wanted to highlight the fact that, like, Tim gave the example of the witnesses disagreeing.
Hmm.
But we know that this is true. We know that, according to Einstein's theory of special relativity, we know that if we're moving at different velocities, we will disagree about the lengths of objects and the duration of events.
Mm,
Um, and so we can come back and we can disagree, but then we can use Einstein's theory to realize that we were just seeing it from two different angles, right?
yeah.
Um, if you can't prove that there's a contradiction, then it's a way out.
I see. I see. So this is relating it to Einstein's theory. And a few moments ago, Mike, you were saying we shouldn't take Einstein's theory as seriously. So like, is this cop
Uh,
out? Should not take it as seriously, or like,
I mean,
what's going
oh,
on with
okay.
that?
We should take Einstein's theory of special relativity absolutely seriously.
Uh-huh.
Einstein's theory of general relativity, we should view it as a very, very good approximation to reality. But there's plenty of reasons why it can't be the exact reality. And this situation is exactly shining a light on this.
yeah. So
W-
I wouldn't
w-
say. Mhm. Go ahead.
one question, Mikey. When you say this is shining, what is this referring to? Is it black holes or
Oh,
just want
black
to
holes.
get?
Yeah, sorry,
Okay,
black holes. Yeah.
got it. Okay,
Mm.
go ahead, Tim.
Yeah, and And I would say that so if you accept this complementarity, and it's okay, it plays well with Einstein's theory, but then it turns out that if you add quantum physics in, this is a major point of contention. It's almost like a head-on collision with two juggernauts. You have Einstein's theory and you add complementarity, and then now you throw in quantum physics. You're like, oh crap! Like something is really off if you
I would
accept
say more
that.
specifically, it's like with Einstein's theory alone, you can use complementarity as what do you call it? As a um, the hell, what do you call it?
Cop out.
Cop out. Yeah, it's
Yeah.
absolutely cop out to Einstein's theory. But quantum, if you add quantum physics, you have to ask the question, what do you mean by complementarity exactly?
Yeah.
That's kind of been the
Uh,
you know
can
topic of
can we
active research.
can we unpack why that's so difficult to answer? Like, why can't you just throw it in there? Like, what's the big deal?
So
What's the challenge?
yeah, so one of the issues with quantum physics is this idea, like we mentioned in previous episode, this idea of the most sacred law, that quantum
Mhm.
physics preserve information, and you can loosely think of information just like a particle carries information, right?
Mhm.
So one of the issues with black holes is that, oh, if you throw a particle inside a black hole, if that particle is just gone, then it seems like information has disappeared, right? That's a big no-no. Like quantum physics just does not allow that, right? And now if you and in some sense complementarity is kind of like trying to fix that, right? Instead of saying that a particle, uh, if it falls into a black hole, information is lost, but you're saying, hey, no, it never fell into the black hole because the interior doesn't exist. It just got plastered on the surface, right? Then you kind of recover that preservation of the information a little bit, right? But then a new problem arises, right? If there are two different realities, right? And then in one reality, the information is plastered on the surface of the black hole. And in another reality, the information is inside the black hole, right? Like if someone is falling into the black hole, they'll see that that particle is in the black hole. Then which one is real, right? Because like relativity wants to give us like a relative answer, observer dependent, but quantum physics kind of demands this like this information, this absolute perspective. There's got to be information somewhere. Now that's the conflict, right? Like quantum physics cannot compromise on the information, regardless of the observer. That's the problem.
So, are you saying information is preserved in like all reference frames for all observers? Is that correct?
Yeah, but beyond that, like there exists
Mhm.
an absolute notion of information, and they all
Mm.
have to agree on that. There exists some information there. Like that's kind of the
So,
conflict.
so you're saying whether or not I'm in the black hole, if the interior does exist, whether or not I'm in the interior outside, we both have to agree on that's there's the same amount of information.
Yes, theoretically.
I think it's
Uh,
true. Every observer has to agree that information is preserved, right?
Yeah, yeah, and,
That's true,
and
right? Yeah.
yeah, and basically in quantum physics, in addition to the fact that you cannot delete information, you also cannot increase the amount of information, meaning that you cannot make copies of the information because if you copy them, you make more information. So you can't just be like, so where's the conflict? Imagine if there's a bird's eye view that's possible, that you can see both the interior and the surface, right? Then you can say, well, what's wrong if a particle falls in? I just make a copy, stick one onto the surface, and throw one to the inside. Then both observers will be happy. Kind of like people on the outside would be like, hey, the information is on the surface, and people
No,
falling
no, that doesn't
in,
work.
yeah, saying that, right? So, but then quantum physics cannot do that. You cannot copy quantum information. So it's either on the surface or not on the surface. So that's the problem now. Like, which one is right?
oh, very interesting. Very interesting. So complementarity is not compatible with quantum mechanics.
At least
It's
on the
not.
surface
It's
level.
not. Yeah. It's gotta be. Yeah. Just yeah. Not in the naive way. If complementarity is the answer, it's there's some subtle way to make it consistent.
I see. So why don't we just say there's like no interior and be done with it and just say that nothing
Be,
actually falls in, everything gets
because
plastered on the surface.
Sahil, at any moment you
Yeah.
could make a decision to actually fall into the black hole, and then when you decide to do that, you eventually see that as you approach the black hole, that everything that was stuck on the surface, you actually see it going toward the black hole, right? If you decide, if you're falling in, like once you pass the event horizon, you see all the things that have fallen in, right? Like there's kind of this transition, right? Like,
But maybe that can't happen. He's saying maybe that can't happen.
Yeah, what if there's no interior? I'm starting to be convinced there's no interior now. What if there's no interior?
Dude, in 2012, most physicists were pretty convinced of that, like that it was impossible. Like, people even question, is it possible to even fall into a black hole? It might literally be impossible. I don't know, like what would stop you? Maybe a wall of
we
fire or
don't know, right?
something.
Yeah. So,
Yeah.
but I would say there's another fact that throws another wrench to this discussion, and that's the aspect of Hawking radiation. Should we talk about that?
I thought you did a good job of not mentioning that and still talking about no cloning.
Let's save that for later then. Let's save that for later. I guess like does this connect with any previous episode like holographic principle, or is there anything with that as a solution to this or
Oh, absolutely. Yeah. Oh,
yeah.
shoot. I'm not if I'm prepared to describe in detail, but yeah, holography is kind of the idea, right? That for those that didn't watch previous episodes, that whatever happens inside of an object uh, can be described alternatively as something happening on the outside. So it has this connection between the interior and the exterior. So holography is like the main tool that physicists use
Yeah.
to think about these things and to try to come to conclusions about this.
Yeah. So basically, I guess the thought is like one way to kind of settle the debate is to say that instead of having to decide whether the information is on the surface of the black hole or inside the black hole, you just say that they are actually the same thing, basically.
What?
But that's,
Wait.
I mean, that's
Oh,
really
go ahead.
hard to imagine, right? Yeah.
Oh, how do you do that? What? That that doesn't make any sense. Like, how can they be the same thing? Is that the same as saying the interior does not exist?
Well, I think we run into trouble when we insist that somehow information has to be localized, right? Like when
Mhm.
we're saying that the particle is plastered on the surface of a black hole means that hey, it's plastered on that one part of the surface of the black hole in some ways, right? And when we chase that particle down into the black hole, we're saying that hey, the particle is here, right? I mean, certainly it makes sense when you're following the particle, like you can probe the particle and measure that it's there, right? But the fact
Mhm.
that there are these two dual viewpoints, it must mean that even though when you observe it, it seems like the information is localized, there must be some sense in which that they are connected. They are one and the same information, right?
What? Wait, when you say information is localized, what does that mean? What does it mean for something to be localized?
Yeah, it just means this very really intuitive sense that like for example, my hand is there, so all the
Yeah.
information about my hand is localized in this location, basically,
Hmm.
right? I can interact with it, I can do stuff with it, right? And if I don't measure this part, imagine
Yeah.
imagine if I hide my hand away, I'll see that
Yeah.
information is gone, right? Like so my
Yeah.
hand must be somewhere. But
S-
mhm.
Yeah. So actually, I don't know if you were talking about this, but I want to mention this point. We were discussing on the episode on holography that like if you imagine like projecting us onto like this, projecting things onto the surface, they may not be close to each other, like in physical space. It might be like this weird kind of like encoded surface. And
Right.
so like what does it mean? Was that what you were getting at, or was that am I
Yeah,
jumping ahead?
Well, just to be clear, holography does not solve this problem by any stretch of the imagination. I mean, in some ways, it kind of makes it worse, right? So holography means that whatever information is in, if the black hole has an interior, holography would say that there has to be a correspondence between the information in the interior and the information on the surface. Um, so basically, they have to be entangled with each other in the language that we've used. But then, if information is also leaking out of the black hole, oh yeah, I guess we got to talk about Hawking. If it's actually leaking out, then this is where a contradiction comes in. So how to make holography consistent with the black hole picture has been a big topic of research.
I see. I think without us like going down a rabbit hole of like Hawking radiation, which we can say for next episode, can you discuss like more intuitively like how entanglement leads to like knowing what's in the inside, what's on the outside? Does that mean if you were the inside the black hole, you could know everything else on the outside of it? What's going on? Is there that kind of like symmetry?
No, no, no. So holography is the idea that if you know what's on the inside, then you know what's on the surface.
And vice
And
versa.
then
Yeah.
yeah, but then also there's this other aspect that black holes have to have a temperature, which is the whole Hawking picture. So if you're on the outside, you have to have some sense of what's going on the surface
Yeah.
too. But then, as Tim
Mhm.
mentioned, if you can't copy information, how can the interior and the surface and the exterior all all be copies of each other? It doesn't make any sense.
Yeah. So basically, the idea that if like if indeed they're separate entities of a particle that exist on the surface of the black hole and in the interior, and that you cannot make copies, then they must be one and the same thing. It's almost like the particle may be in two places at once. Or maybe that it's not really that the particle is in two places at once. It's just that our notion of where that particle is flawed, right? Like the fact that the particle has to have a location, maybe that's flawed, right?
Hmm. So does that mean that the information is in two different places, or because I'm trying to resolve this contradiction of what you talked about between like complementarity not working with quantum mechanics, how like you can't have clone the information in two spots, but clearly there's like a difference between the interior and exterior if the interior does exist. So I'm still trying to like wrap my arms around that.
Hmm. You can have information spread out at most like two places. Like two particles can basically have the same information if they're
Hmm.
entangled exactly.
Hmm.
Um, but you can't have three places having exactly the same information. And so if there's an exterior, a surface, and an interior.
Hmm.
There's three regions that have to have basically the same information. And this kind of violates the no cloning theorem, which says at most a pair of particles can have this. They're not clones of each other. That's not the cloning that Tim used, but
Hmm.
information can be spread out in two different places. But you can't copy that information to a third place.
So I guess like one thing I want to ask is, so if we go to the example where you have like information in two separate places with two, let's say two particles entangled, is it the notion that like if you know the state of one and they're perfectly entangled, you know the state of the other. So if you know the information of like one configuration and it's like perfectly entangled with another configuration, then you would
Mhm.
know like the information of that configuration. Is that what you mean by like,
Exactly. It's
okay.
exactly, yeah.
Yeah,
But
exactly.
there can't be a third one here. Lenny Susskind likes to say, entanglement is monogamous. You can have it,
Uh
particles can at most be married to one other person, one other particle.
ah, I see. I see. So the crux of this is that you have this like same information in like three different places: the interior, the surface, and the exterior. And it's
Yeah.
like, what gives? Why is that happening?
Yeah. It means the surface is a weird place. Like, right? Like that's like the third person at the party that no one invited. It's like messing everything
Does
up.
but the surface seems ambiguous in some sense. Like
It
it,
is,
it
but
does it even like really it seems like more of a artificial construct based on mathematics that we say at this point is the point of no return, but there's no actual like surface that I can stand on, or like it's not a hard boundary in some sense. Is
I
that
would say
fair?
it's a harder boundary. Like the surfaces that we stand on, those are not hard boundaries. You can break those. But the boundary to black hole is like the hardest boundary that even light can't go through it.
yeah, but I
Or
think that there's a bit of point of contention, right? There's perspective that you're not gonna feel a thing as you fall into a black hole. But then, if you truly believe Einstein's theory, but of course, if
Hmm.
you think Einstein might be wrong, then this might be modified. You might actually feel something as you fall through the point of no return on a black hole.
the no
Yeah.
drama postulate.
So I guess coming back to our original question, like, does an interior exist? can we like tie this all together and sort of like see if we can answer that question, or like what is your perspectives on that in the remaining time that we
I would say that we can't answer that because it's but
have?
we can say for sure that if the interior exists, it's not encoded in the same language as the exterior. There's something complicated that happens on the surface that we don't quite understand, and it's not like a regular object where you can just pass through it and describe the interior the same way you describe the exterior. Something happens at the surface,
Mm,
something very strange and very weird. Uh, Probably looks like some kind of encoding, some kind of change of in the way the information should be viewed. Very strange.
Yeah.
so what, sorry, Tim, one thing I want to ask Mikey is that, so what you're saying is like, to kind of go back to the Einstein picture, you're saying it's not as simple as like you pass through and there's like nothing with blackness and you just like there's a singularity point. It's something completely different.
Yeah,
Like
I mean, if
very,
I'm if,
very
if
different.
I'm betting on it, I'm not putting any money on that one. That seems very unlikely now that you pass through and it's just that simple. There's something, like another universe and encoded in a different language or something crazy like that. Black holes are very crazy.
Yeah,
Gotcha, gotcha.
basically, the black hole is the most extreme information scrambler of the universe, right? So as you fall into the black hole, we really don't know how your quantum information is going to get rearranged, you know, and they can get rearranged, reshuffled, probably not copied, but entangled in some super strange ways. And that
Yeah,
part is we still have no clue. But these are but the crazier thing is that black holes are real, and there is a real
Mhm,
answer, and this is part of nature, right? Like
mhm.
nature is doing some insane things, and I bet you the truth is probably crazier than any science fiction that we can imagine, probably.
for sure. Which
I
makes it
see.
exciting. How often can you say that?
Yeah.
Yeah. So, last question for you both, and this is gonna enter in purely speculative territory here, like extremely speculative. What do you guys think is going on with black holes? Like, just even if it's completely dead wrong, like, just your gut. Mikey, you go first.
I think that when a black hole forms, it's the birth of a new universe inside of the black hole.
Oh, shit.
I mean, probably there's already an alternative universe, whatever. Well, if you can call it that. I would buy into the complementarity idea, right? Like you go into the black hole, you're gone. Okay, for you, it's a new world. For the people outside of you, well, sorry, like I mean, but to some extent, you still exist. You still exist in the old universe, just scrambled up in some ways. But for you personally, you have a whole new world to explore, kind of, you know.
All right.
I
Well,
think that oh wait, I think that when a star explodes and creates a black hole, from the inside of a black hole, I think it looks like a Big Bang. Is that too crazy?
it's a speculative time, man. You can make
I
it
don't
as
think anyone.
crazy as you
I don't think anyone can argue why that's wrong effectively.
want. It
Final
is.
answer.
It does seem pretty violent of a process when a star collapses into a black hole. Yeah.
So it's a Big Bang.
Yeah. All right then. Anything else, Tim and Mikey, before we head out?
uh,
Yeah,
well,
I
I
think
would
that's it for
say,
me.
yeah, I would say black holes are super fascinating objects, and this is still in the scientific frontier, so we can't really tell you much more than that. But this is an intriguing question, and it's not just about black holes either, because the answer tells us something about the way quantum information is structured. It tells us how, space time is organized, right? Because, you know, and it challenges our fundamental notion that things exist in a particular location. Even that notion could be wrong in the face of a black hole. And if that's wrong, then it was never right to begin with, right? So it's a fascinating topic, and I think I'm excited to see what researchers come up with.
Yeah, I'm excited too. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
See ya. Bye.
Yeah.